Hello, my name is Anthony Atkinson.
And my name is Marco Riani.
We are the co-authors of a new and exciting book on robust regression. You can see that we have three co-authors, but Marco and I have been working together on this for over 30 years. The others are relatively recent.
We are here in order to give you a comprehensive analysis of a dataset which is called the AR regression data. This dataset is made up of 60 observations and 3 explanatory variables.
In our book, these analyses occur in a variety of chapters to illustrate various properties of our form of robust regression analysis. But in this video, we're going to go straight through and just concentrate on the analysis, taking calculations from a variety of chapters.
We start with the scatter plot of y against the different columns of x. Here, as you can see, there seems to be a strong linear relationship between x2 and y, same thing for x3. On the other hand, it is not so clear what is the relationship between y and the first explanatory variable.
However, there don't seem to be any gross outliers shown in these plots, for example.
We start with the fit based on all the data. The R-square for this fit is very high, equal to 0.965, which denotes that the 3 explanatory variables indeed explain a lot of variability of the response. What do we see about the p-values of the explanatory variables? There is one variable which is not significant, the Hughes coefficient is negative, and the 2 other explanatory variables are very significant. Now, let us check the residuals. And now we have a 2-panel plot. We have on top the studentized residuals, and at the bottom we have the deletion residuals. In all our plots, all the bands can be shown or hidden. And here there is one observation, 43, which is just outside the 99% confidence bands. The traditional way of working is to produce additional plots, and now a common plot is the qqplot of studentized residual. Now I leave Anthony the floor because he is one of the people who invented the qqplot of studentized residuals.
That's right. Under the influence of Brian Ripley, I produced this, if anybody remembers Brian Ripley. So the simulated confidence intervals have to be simulated because of that they depend on the values of x. We can see that just about everything lies inside. Down at the left-hand corner there is observation 43. Otherwise, there seems to be no evidence for outliers for that.
Well, but observation 43 is fully inside this.
It is fully inside, yes.
It's fully inside this band. And the plot of the residuals against fitted values confirms the absence of outlying observations here, and maybe that there is this observation 43 which is suspicious.
Mm-hmm. Just to a thought about the envelopes. They are 95% envelopes.
Yes.
So if you simulate 60 observations, you might expect to get 2 or 3 outside of them. So,
right.
So these residuals really seem to be behaving very well.
Given that observation 43 is a bit suspicious, then we try to see what happens after removing observation
43.
The R-square has slightly increased, and the significance of the first explanatory variable has increased. Now it is at the boundary of significance.
In our succeeding analyses, I hope you will pay attention to what is happening to the estimated coefficient for x1. It's really quite interesting.
Now notice that these explanatory variables has a coefficient which is negative and almost significant. Now we move to the traditional robust analysis, that is the analysis based on S-estimators. And in these S-estimators you have to fix the breakdown point. So we see on top the analysis of the residuals, which are based on a value of breakdown point which is 0.25. And at the bottom you see the residuals based on a breakdown point 0.5. You do not expect very much difference. You do not expect that the result may depend on the particular value of breakdown point that you choose.
Why don't you expect that?
Because they are so-called robust estimators and therefore the choice of the particular value of the breakdown point should not matter.
Mm-hmm. However,
in this case, you can see that while with the value of breakdown point of 0.25, we have a picture of residuals which is very close to that of studentized residuals, in the sense that observation 43 appears as outlying. If you use a value of the breakdown point equal to 0.5, you can see the presence of several outliers. On top of that, you can also see that there are a lot of units which are at the boundary of significance. Indeed, in this example, there is a very big difference between the analysis carried out with these two common values of breakdown point.
Could I just say that in our descriptions of some of the other chapters, it will become apparent the asymptotic size of these tests for really quite large samples, even several hundred observations, can be very far from what one would like. This seems to be an instance of that here, this huge number of outliers that have suddenly emerged.
We claim that this is one of the reasons why traditional robust estimators have not become the default, as one would have expected 50 years ago. Now, we move to the analysis of estimators. We consider two values of the nominal efficiency. In the top panel it is 0.9 and the bottom panel it is 0.95. There should not be such a large difference. On the other hand, we see what we had seen before.
Mm-hmm. And we will see this carefully quantified when we look, well, you will see it when you look at the video for chapter 5.
Now we move from this, what we call static analysis. In this static analysis, you don't know whether observation 21 is linked to observation 47, if these observations which have large residuals form a group, if there are hidden groups, and in general, with this static analysis, you don't know the effect that each unit exerts on your model, independently of the fact that one unit is outlier or not. Mm-hmm. We need to have not a snapshot of the data, but we need to have a movie of the data. Now we are going to show you the typical plot of monitoring of the scale residuals as a function of the subset size. For example, 20 means that here there are 20 units inside the subset. We click on 20, then you can see the trajectories of the residuals because each trajectory corresponds to a unit. These are the 20 units which are inside the subset step 20. These are those which are inside the subset step 33, then we have 41, then we have 45. This unit has a residual which tends to increase as the subset size grows. Moreover, what do we find on top of here? Here we find that there are trajectories which are reacting in the same way to the introduction of units inside the subset. When these units start to be included, then this is observation 43, the one which has the largest negative residual is excluded from the subset, and this observation is included again in the final step. So this is an example of analyzing a movie rather than a snapshot of the data.
One can see that at the absolute end of the search, that is at least squares, there's just a general mess of residuals with no particular structure at all.
Now see what we can do. Here the plot of residuals is presented with the different colors. Note that this plot is slightly different from the previous one because the initial step of the search might slightly depend on the initial subset, but
which is chosen to an extent randomly.
Partially randomly because we search over 3,000 subsets, but the final part of the search is completely unaffected. And here you see the presence of a group of units with very large residuals, and then the residuals for these units is completely mixed with that of the other observations when all units are included. All our plots are brushable in the sense that you can select these units and then you can see their position in the yXplot. So these are the units that have been selected. These units do not appear as outline in these bivariate projections. They seem to lie inside the bulk of the data, and there is no possibility by eye to say that these units are outlying in some way. Now, let us see a three-dimensional scatter plot, where we have put a red dot for the 6 outlying units, and observation 43 has been marked with a black dot. Of course, a 3D plot depends on the angle. And now look at this angle. In this angle you can see that the 6 outlying units lie in the bulk of the data, but they lie on a different hyperplane.
It's interesting, these projections or rotations, that you really need to watch it being done, and then you really get a sense of the spatial orientation of the observations. Whereas if you look at one, well, that's a good one actually. If you look at one plot, you sometimes can't see things quite so clearly. A limitation, a regrettable limitation, of course, is that they're three-dimensional plots. So if you have more than 3 explanatory variables, you can't include them in the plot.
Finally, it is also worthwhile to notice that observation 43, that is our observation with a very large negative residuals, there is no 3D angle in which this observation appears as outline. Here it is important to monitor residuals, but also to monitor the t-statistics. And now we go back to the problem of the importance of the variables. In the traditional table, you just see the final value of the t-statistics when all the observations are included in the subset. So this is the search, subset size, and then these are the values of the t-statistics for the 3 explanatory variables. And you can clearly see that the sign of the first explanatory variable is positive and significant, and then when the outliers join the subset, the 6 outlying observations join the subset, the t-statistic for this explanatory variable passes from being positive and significant to negative and almost
It's not significant when all the observations.
Yes, the sign changes and the degree of importance changes when these outlying observations are included into the subset. The exclusion of observation 43, this final thing that we had seen before, is just a small step in this monitoring of these trajectory. On the other end, the trajectories for the variables x2 and x3 are always highly significant, independently of the fact that the outlying observations are included or not. We now analyze what happens to the residuals when you consider 50 values of the breakdown point. Now we consider the monitoring of S-estimators when we consider a power divergence of function. So with the power diversion, everything is very, very quick because in order to have 50 fits, it takes just 2.5 seconds. If you use the optimal rho function, 50 fits take almost 4 seconds. If you use the hyperbolic rho function, given that the hyperbolic requires a lot of iterations in order to find the tuning constants, then the hyperbolic requires much more time. Then we have a optimal rho function with the different expression for the variance covariance matrix of the beta coefficient. Now, after doing all these calculations, we are ready to see the results. And on the left, you have the monitoring of S residuals using the optimal rho function for 50 different values of breakdown point, from 0.5 up to 0.01. On the right, we have the correlation coefficient between two adjacent values of the breakdown point.
These correlations between adjacent residuals do indeed show a very sharp trough, peak I suppose you could think of it as, just when all this vertical stuff is happening at around breakdown point of 0.27 or something like that.
Yes.
And they also show adjacent correlations changing a bit further back at about 0.36. There are smaller dips there.
Yes.
In general, we have found that the study of these correlations is very powerful.
This is what we call the power of monitoring, in the sense that you can see that this set of residuals reacts in the same way. So these units are in some way related to each other. They form a group. Then there is observation 43 as a residual which is completely in line with the others for high values of breakdown point. But residual for these units increases when the values of the breakdown point are inside the range 0.25. Actually, it is very different in this case to use a breakdown point of 0.25 or a breakdown point of 0.29. So this movie lets you understand what is the effect that the different use of breakdown point has on your fit, on your residuals. And moreover, it lets you understand that there are subgroups in these data sets and which observation is connected with any other observation.
The last half of this plot from 0.27 or something onwards is very close to being the least squares fit. It's, we find in many of these plots that the robust regression breaks down at some point of efficiency or breakdown point to being close to the least squares fit. And another thing, of course, is that here you have to have a breakdown point of 2.8 or something to get a robust fit, whereas if you use the forward search, you get a much larger subset, larger effective subset for doing the analysis.
Then if you wanted to click on a particular trajectory, then it is possible to have additional information about this unit and the the weight that it has. So far, we have analyzed the optimal rho function. Then you want to see whether you have different results if you use a different rho function, such as the ample rho function. And you can see that the results are very similar as those that we had before.
Of course, the results are also in a way very similar to least squares, aren't they? It's just that the horizontal scale, which is very important, has been changed by the different analyses.
And now the hyperbolic, and then once again you see that there is this observation 43 that is all of a sudden, then when these outlying observations have a certain non-negligible weight, then observation 43 starts having a residual which is large. Then our power divergence rho function, and then also in this case there is no appreciable difference from the use of this rho function and the use of the other rho functions. This power divergence rho function has the additional benefit that it has an explicit expression for the breakdown point given a particular values of the parameters, does not require iterative procedures.
And it just has one parameter, is that right?
Right. Now, I think it's time to come to the conclusion for this data set.
I think, again, as we shall see, or you will see in some of the other analyses, because you can fit a regression model and not get any particular patterns of residuals or of significance of variables, doesn't mean that everything is fine. You really do need to dig into the data and use these robust methods monitoring of the forward search to find whether there are clusters and unexpected structures in the data.
And moreover, with this approach, you can see what is the effect that each unit has on your model. This is exemplified for regression, but these concepts apply to any other model. Thank you for watching.
Yes, thank you very much. Goodbye for the moment.
Goodbye.